This week we are covering frequency response, and we'll cover parts in red this week, and we'll cover the Bode plot, poles, zeros, the Miller's theorem. This is a typical frequency response, and typical frequency response means, as I mentioned, amplifier. You usually, when we ask you until so far, what is the gain, you measure the gain, right? For instance, for a common emitter, GMRC. Well, yeah, this is GMRC is the gain, but usually it's the gain here at the midband. So what if at the lower frequencies or higher frequencies? Actually that's not the same gain. And the reason is we have a lower corner and a higher corner cutoff frequency. And the cutoff frequency defines where your circuit basically operates. What we do is we apply a sinusoid signal into the input. You can do that in PSpice, and just like 5 sin omega t, or you can just make the amplitude variable and you can just apply it to the inputs, and you can change the voltage. Then that shows the linearity of this amplifier. Linearity means how your circuit responds with increasing voltage. Eventually you won't be getting the same gain. Now we are looking at sweeping the frequency. What if we sweep the frequency? Will I get the same gain? So as you can see, we increase the frequency at the input. Well, supposedly I should be seeing the same gain, right? But no, my gain is much smaller. So output signal is much smaller. Well, because as you can see here, the circuit rolls off. Here, it's like this, but some circuits, it might be this, depends on the circuit. In this case, we have a cutoff frequency pole at F1, which means a cap inside the circuit, basically not letting you get gain at increasing frequency. Because this frequency omega basically somehow inside a circuit through a capacitance going through the cap, because omega is big, this is big, so 1 over big is small, so it sees a small impedance and loses the signal, right? If you apply a signal and ground here, will you get signal here at the output? No, right? Because this cap at high frequency shorts your signal, right? That's why when we look at the characteristic V out over V in transfer function, at this cap causes signal drop or roll off. And the reason we usually use sinusoids, because every signal is a summation of different sinusoids with different frequencies. A square wave is sum of sinusoids. It is sine omega t plus 1 over 3 sine 3 omega t, something like this, plus it goes on 1 over 5 sine 5 omega t. Maybe it's not exactly like that, but it's sum of different sines. So every signal at the input, this is called Fourier series, is represented by different sinusoid signals. So that means, your circuit, for instance, this square wave at the output, maybe your circuit will get this, right? Because you have a gain of AV, but maybe if it's a very high frequency signal, let's say this is 60 gigahertz. So let's make this 70 gigahertz, okay? So 60 gigahertz signal, you'll get gain 8, but 3 omega, 180 gigahertz, 180 somewhere here. So this is dB, okay? So that means this is 0 here. So this is 0 dB means you multiply with 1, okay? But this is not minus gain. This is minus. So, you gotta, what is dB? 0 dB means 20 log 1. The AV is 1. So here AV is the gain. So 0 dB means gain is 1. So minus 50 dB means gain is not minus 50. Gain is minus 50 dB. That means, 20 log gain is so small. This is 10 to the minus 5, okay? So don't confuse this part. It's not minus. It is so small value. Anyways, at 180 gigahertz, the gain is so small. So at the output, what would you see? You apply a sinusoid signal, okay? And you are looking at the output. Which of these would you see at the output? Kare sinyal var. Bu kare sinyal aslında farklı sinlerin toplamı. Sin omega t artı 1 bölü sin 3 omega t artı 1 bölü 5 sin 5 omega t. Kare sinyali 3 tane veya 10 tane sin'in toplamıyla farklı frekanslarla represent edebiliyoruz. Şimdi bu kare sinyali transfer karakteristiği bu olan bir amplifier'a yükledim. Şurası 70 GHz ve benim input frekansım şuradaki sin omega frekansı 60 GHz. Yani aslında kare frekansı, karenin, hatta buna bir digital bit olsun, 10 olsun. Frekansı 60 GHz.
O zaman sadece ilk sinüs geçer. Çünkü diğerleri 0, yani AV 0 olduğu için gain yok olur. Sadece sinüs omega t geçer.
Aynen öyle. 60 GHz'de AV gain'ini görüyor, 60 GHz. Ama 180 GHz, şurası 5 omega t'de, 300 GHz. Gördüğünüz gibi gain çok düşük. 300'de de çok düşük. Dolayısıyla output'ta bunu görmüyorsun. Çünkü şu demin anlattığım artık kapasitans tamamen neredeyse short o frekanslarda. Yani o kadar büyük frekans ki bu kapasitans birazcık büyükse, çok küçük bir kapasitans değilse 1 over j omega c burayı neredeyse shortlayacak. Dolayısıyla bu yüzden şöyle bir kare sinyal output'ta bir sinüs olarak görünce şaşırmayın. Mesela yüksek frekansta. Bunun nedeni bu roll-off. Okay? Let's continue. Mesela güzel bir örnek. Natural voice. My voice is, or your voice is between the range of 20 Hz and 20 kilohertz. Okay? But when you talk on the phone, because of the equipment in the cell phone, there are chips, right? Your voice is constrained between 400 and 3.5 kilohertz because it's really hard, to get 20 hertz signal through your cell phone chip, because then you would get the noise. There is a lot of noise here, and you wouldn't want to get the noises in the background, so you started from 400 hertz because basically you get rid of this part of your voice. Anyways, therefore, your voice in the phone differs from face-to-face conversation, değil mi? Telefonda sesinizi dinleyince ya bu benim sesim mi? Nasıl olur diyorsunuz. Çünkü frekansları farklı. Yani 20 Hz'ü artık telefonda duymuyorsunuz. Mesela başka bir örnek. Question for you guys. Similar. Your voice goes to the voice recorder veya your voice to the human ear. Mesela bu niye farklı? Yani ben konuşuyorum ve kendi sesimi dinliyorum şu anda. Veya şu anda record ediyorum mesela. Sonra bunu Panopto'dan dinliyorum ve tamamen farklı geliyor ses.
Speaker'ın da belli bir büyük ihtimalle seviyesi var. O da kırpıyor olabilir.
Aynen öyle. Sadece speaker'ın değil. Mesela ben şu anda konuşurken sesim nereden gidiyor? Bir havaya gidiyor. Havadan kulağıma geliyor. Bir de kendi içimden, beynimden aslında sesin bir kısmı da aslında dışarı çıkmadan beyinden, yani iskeletten kulağa gidiyor. Aslında 2 tane kanal aracılığıyla tekrar kulağıma geliyor. Ama recorder'a gittiği zaman recorder'a sadece mesela hem Emin'in dediği gibi recorder'ın da bir speaker'ı var ama aynı şekilde recorder'a sadece air'dan gidiyor mesela, değil mi? Dolayısıyla sesin travel ettiği kanal, the environment, the voice travels, here is air and here is air and skull. So they will have different, just like I explained in that square wave example, they will have different characteristics so that at the output, you will hear different voice, okay? Another example in the image processing, this frequency is not just for voice, right? Every data has a frequency. So mesela high bandwidth'i olan bir sistemse, high bandwidth ne demek? Bütün sinyalleri alıyor. Şuradaki bandwidth yüksek. Low bandwidth ne demek? Olabildiğince kısıtlı bandwidth'i var. Yani kesiliyor mesela şurada. Dolayısıyla similar with the image, these things can be represented as these pixels. Actually, when you see it through the camera, there are CMOS imaging system, right? This is actually signal, and this signal, these are, this is the color, for instance, and this color is detected through circuits. And when you see it in the camera, this picture and this picture is because of the equipment, the technological circuit behind it. Like, a high bandwidth circuit lets the entire, data let go through, but a low bandwidth, of course, because of the insufficient bandwidth, the sharp edges become soft, right? Because sharp means, like, basically in time domain, a sharp, or in the image as well, something sharp in time domain. What is the frequency of this part? Can somebody tell me? This is the time domain. Sorry, T is here. This is amplitude. So in time domain we have an impulse. What is the corresponding in frequency? Time domain'de bir impulse var. Şöyle diyeyim. Time domain'de
horizontal line.
Aynen. It's a white, like it's unlimited bandwidth, right? So this one has unlimited frequencies inside this impulse in time domain, because you can, if you want to draw this in time domain, this impulse, you have to draw all the different frequencies. It's hard to explain, but this impulse in time domain is, as Hakkı mentioned, is a line in frequency domain. Şöyle bir şey olsa time domain'de, düz bir line'ınız olsa DC sinyal, o zaman frequency'de ne olur?
Impulse.
DC'de bir impulse olur değil mi? Aynen öyle. Şimdi aynı mantıktan şu sharpness, time domain'deki sharpness veya bu image'deki sharpness. Gördüğünüz gibi frekans olarak inanılmaz fazla data içeriyor. Dolayısıyla sharp bir sinyali siz geçirebilmek için şöyle bir sinyaliniz varsa devrenizin bandwidth'inin bayağı güçlü olması lazım. Değil mi? Unlimited bandwidth'li bir sinyalini geçirmek istiyorsunuz input'ta. Frekans domaininde bu. Dolayısıyla eğer bandwidth'inizin bir roll-off'u varsa şu amplifier'ınızın belli bir sinyal geçemeyecek. Yani şu impulse'ı, şu sharpness'ı alamayacaksınız. Değil mi? Dolayısıyla gördüğünüz gibi böyle soft'lar olabiliyor. Yani sharp edge'leri alamıyorsun. Bu bir mesela hayvanların miyavlamasında da olabilir. Mesela bazı veya hani mesela köpeklerin köpek whistle denen bir şey var. Hani we cannot hear it, but dogs can hear it, right? Well, because our ears cannot get that frequency. That whistle, our ears cannot hear it because our ear is a circuit with this characteristic. But that whistle frequency is somewhere here, right? So that's why we cannot hear the whistle. But dogs can hear it because their ear probably is like this. So they can hear the whistle. Okay? Any questions? No? Cool. All right. So, now this is the term called low pass filter, high pass filter. So, logically, just when I tell you, hey, draw a low pass filter, like without a blink, you should be able to draw this, right? Why? Because at low pass, what is this cap? Like at low frequencies?
Open,
right? Because it is 1 over j omega c. So if it is low frequency, just take the DC as an example. This is 1 over 0. So it's infinite impedance, which is open. But whatever input shows at the output, right? There is no leak anywhere. So that's why V out over V in is 1. But when you start to increase the frequency, then this impedance starts to become what? Short. So at infinite frequency, this is short. So V out is short to the ground. I mean, not necessarily ground, but this is short basically. V out is 0, right? So if this voltage is 2 volts, well, this is 2 volt too. So V out is 0. Well, that's why V out 0 means minus dB, infinite dB, minus like what? 100 dB, okay? So, okay, so that's basically what is a low pass and high pass. If I ask you, hey, knowing this is a low pass, design a high pass, what would you do?
change the resistance and capacitor.
I know, okay. So exactly. So we gotta reverse this R, it should be C, and this should be R. Why? Because this C, DC cannot pass, right? So it is like that, this cannot pass, but high frequency, it is short, it can pass. And at very high frequency, this is short. So whatever here will show here, right? So that's why at certain frequency now, you get the transfer characteristics of 1, okay? All right. So now let's look at the gain roll-off of a common source. So in the past, you guys just were calculating the gain, right? And the gain was simply the one here at the bottom, GM times this. Basically, when we divide V out over V in, right? The V in cancels, and this becomes gain. But now, this cap is actually the capacitive load is the one that causing gain roll-off, because as we mentioned, at high frequency, it will steal away some signal, which means at high frequency, this impedance is small, right? This cap impedance, because it's small, the current here, the GMV in current, minus of it will go here, and it will, if there was no cap, all of them would go here RD. I'm assuming RO resistance, this one is infinite, okay? So it will go RD, but because there's a cap, the higher the frequency, this current now will sneak into the cap. So the cap will steal your current. That's why the roll-off happens, because if the current doesn't go through the R, but C, well, I don't see any gain, right? So eventually this impedance becomes what? It becomes at high frequency, it becomes short. At low frequency, it becomes RD, right? This is my output impedance, RO, big RO, RD parallel cap, right? So this cutoff or roll-off is basically a frequency called 1 over RC, angular frequency, so omega. Okay? So at the certain specific frequency where it is omega 1 over RC, I start to see 3 dB, which means the gain drops by square root 2. Okay, so why is it 3 dB? If you do 20 log this, 20 log this, it is A minus 3. Okay, so that's why you lose the gain by 3 dB. So 20 log 1 over square root 2 is minus 3 dB. Okay, so this part, the frequency, angular frequency 1 over RC, causes this voltage drop by 3 dB. So, and the entire frequency is actually frequency response is basically modeled by these caps. So these transistors have tiny small parasitic caps, and those parasitic caps define, remember I draw this, those small parasitic capacitances define these parts, and these external big capacitances, I might put one here and then I might put one output. And these big capacitances, because they are big, right? Because they are big, that means 1 over RC is small. Then it defines small poles or changes. Okay, so and these parasitic capacitances are so small. Because they are small, that means 1 over RCs are big. Okay, there is a gap here, parasitic between these two nodes, and there is a parasitic gap between these here. Okay, so the brown ones are the caps we actually don't see it, but they are there. Okay, and they are small, and because they are small, 1 over RC is big, but it's still there. 1 over RC is there, so there is a 1 over RC here, or there might be another 1 over RC here. Okay. And the other ones, as I mentioned, due to the big external caps, they define here. So we basically represent this frequency response as 3 terms: mid gain, A mid, and high frequency terms, F Laplace high, and low frequency term, FLS. Okay. So this FLS, when the frequency is high, basically, your circuit can be just represented with this at high frequency. At low frequency. At high frequency, your circuit can just be represented like this, because this one goes 1 when the frequency is high, and this one goes 1 when the frequency is low. Okay, so basically we divided this entire characteristic into 3: FL, A mid, F basically low frequency, mid gain, high frequency. Okay, which I will explain in the next lectures. So let's continue with the a little bit more bandwidth and some other concepts. So this is a common source stage, right? Just like the previous circuit, which was this one. So it explains what I explained a bit more detail. So it will be just again explaining the same thing. So as I mentioned, there is this resistance, right? RD and CL. So as I mentioned, this is the angular frequency where you see the 3 dB roll-off. Okay, and this part is called 3 dB bandwidth from 0 to this frequency 1 over RDC. So this is called 3 dB bandwidth, and this is actually where we benefit from circuit, right? So we don't really care this other part. This is why we care, because this is what the linear portion is. So if you apply a signal, square wave signal, and as you see, this frequency is 60 gigahertz. Well, at the output, I couldn't get my square, right? It is completely different. It's sinusoid. And why? Because circuit is not capable to get gain at the other 3 frequencies or 5 frequencies, right? So we actually care about 3 dB bandwidth. If the 3 dB bandwidth of the circuit was 500 gigahertz, which is a lot and not possible, well, then it would let other components of the sinusoids, and then we would see a square wave, okay? But no, this amplifier has a 3 dB bandwidth of 70 gigahertz, as we gave the example at the beginning, so that we couldn't get the other frequency, right? And when we look at the V out over V in, you can see that this is the gain. And why this is the gain? Because at the numerator, we have actual gain, GMRD, right? Just like the gain when there is no cap. And at the denominator, you have the pole. Well, what is the pole? it is 1 over S omega, and this is the GMRD. So at the frequency, this S is J omega, right? So you can write this as 1 plus, and this is 3 dB. Let's call it V1. So this is J omega divided by V1. So when the frequency omega is V1, the denominator becomes 1 plus J, right? Because omega, they cancel. This becomes 1 plus J. Well, and that becomes in magnitude square root 2, right? So that's why 3 dB is there, at that frequency, that's square root 2. Well, if you would take the magnitude, basically you take the magnitude of this, right? And then you get that. Basically 1 plus J, 1 over RD, you put 1 over RD here, RDCL, then 1 over RDCL flip. So you'll see 1 plus J RDCL omega. And when you take the absolute of it, you take that, okay? All right, so here it's basically, if you didn't understand, you can check Razavi. This explains nicer. Same circuits. This is the gain. You write it in terms of Laplace transform, and we replace S with J omega. And when you want to take the magnitude of it, you can write it like this. So kompleksleri hatırlıyorsunuz değil mi? Mesela Kaan, what is the magnitude of 4 plus 3J? Hangi Kaan? Kaan Gürer.
Efendim hocam.
Bizde misin?
Evet.
4 art 5 bir Türkçe bir İngilizce dönemedim. What is the magnitude of
5 değil mi?
Yeah, exactly. So why? We're taking square of 4, taking the square of 3, and then we are square rooting it. Well, same thing here, right? We are taking the square of 1. We are taking the square of RD, CL, and S was J omega, so omega J. So basically we are taking the square of this one, right? And that's what here. Then we summing them up and square. Okay, thank you, Khan. So that's why it is the value here. And this one, should be equal to here at a frequency. This one is square root 2 and GMRD. And that frequency gives basically this is the proof why it is 1 over RC. And that frequency is your cutoff or rolloff. And when you solve this for omega, you find that your 3 dB bandwidth is actually that frequency, 1 over RC. Okay, so if you are wondering why it's 1 over RC. Basically gain'in kök 2 düştüğü, yani gain bölü kök 2 düştüğü yere bakıyoruz. Bunu ona eşitliyoruz. Oradaki frekans omega, yani 2 pi f frekansını çekiyoruz. Onun 1 bölü RDCL olduğunu buradan da kanıtlıyoruz. In general terms, the circuits have something called figure of merits, FOM. And this metric is basically showing in general how circuits are good. And good means basically there are different figure of merits. And people define this figure of merit. If you want to measure the speed, you need to create a figure of merit that basically takes from the speed qualities of the circuit. Well, here, when you look at this one, for instance, it tells you the figure of merit for a circuit gain, bandwidth, and power dissipation. And in the bipolar case, low temperature and load capacitance mark a superior figure of merit. So in this case, probably in the next lectures, it might explain a little bit better. This circuit has a figure of merit as gain, bandwidth, and power consumption, because all of them are important. You want the gain to be big, you want the bandwidth to be big, you want the power consumption to be small, right? So a figure of merit should be big, right? That's why it's called figure of merit. You are comparing different architectures. So if the gain is big, bandwidth is big, power consumption is small, that's a great circuit. If it is not, figure of merit is small. If it is good, then figure of merit is good. Well, for this circuit, simple BJT amplifier, you apply input to the base. This is a common what amplifier? Anyone?
Common source.
There is no source. There is no source here.
Sorry. Common drain.
Gelecek drain de yok BJT'de. Aşağısı neydi?
Common emitter.
Emitter.
Aynen. Common emitter amplifier. Input base'den, output collector'dan. Şimdi bunun figure of merit'ine bakıyoruz. Gain. Şurası GM, IC over VT çarpı RC. Bu senin mid gain'in. Yani frekanstan bağımsız olarak gain'in. Bandwidth'i demin bulmuştuk. Şuradaki impedans R ve C'nin 1/'sü. Cutoff frequency yazdık. Power consumption voltaj çarpı buradan geçen DC akım. Yani ICC çarpı VCC. Bunları yazdığımızda böyle bir şey geldi. Bu çok mantıklı. Yani neden farklı? IC'ler birbirini götürüyor vesaire. Şuradaki VT zaten sabit. 25 millivolts. VCC is your supply voltage and CL is your output capacitance. Şimdilik burada CL olmadığını düşünelim. Yani daha doğrusu output CL yok. Ama devrenin, transistörün kendi parazitik CL'i var. Birazdan onu anlatacağım. Her devrenin tabii ki bir kapasitansı olacak. Dolayısıyla aslında baktığınız zaman bu devrenin figure of merit'inin iyi olması, voltajın, supply voltajın ne kadar küçük olmasını, değil mi? Bunu ne kadar küçülürseniz figure of merit'iniz o kadar büyüyecek. Ve şuradaki CL kapasitansı, if it is small and if VCC is small, your figure of merit will go up. Okay? Well, I can define a different figure of merit. I can put here something like, I don't know, 1 over noise, okay? Or, noise küçükse mesela benim daha iyi bir noise, low noise amplifier'ım demektir falan filan. Yani farklı bir figure of merit yapabilirim. Ama bunun için mesela gördüğünüz gibi VCC ve CR küçükse bu demektir ki iyi bir figure of merit'i var bunun. Okay? Dolayısıyla ileride karşılaştırırken bir işte şirkette çalışırken vesaire bir product'ı başka bir product'la karşılaştırırken belli figure of merit'ler belirleyeceksiniz veya piyasada o figure of merit'ler olacak ve onları kullanarak karşılaştıracaksınız. So this is not just for circuit design. So figure of merit is used for every comparison. Dolayısıyla you guys have this figure of merit for everything. Even when you find a good car, well, it should have a figure of merit. Acceleration, gas consumption. So anyways, so you got the point. And circuits have this figure of merit. Now we'll look at important concepts between frequency response and step response. And after this, I'll take a break. So you should understand the correlation between frequency response and time response. Şimdi mesela bir time domain RC circuit bir voltage var. RC. Buradaki kapasitans 0 volt and it is charging, but it's charging through a R of like what? 1 million ohm. Çok büyük bir impedans. Kapasitans nasıl charge olur? Is it charging like this or would it be charged like this?
The second graph.
It would be charging like this, right? Because this R causing this cap, this current be so small. And because current is so small, the charges on this cap would take forever collect Q equals CV, right? So eventually, this cap will come to a voltage, steady state voltage, but because this current is so small, we can also write it in terms of current times time, or let's write it as integral, I times dt. Well, long story short, because this current is so small, it will take, regardless of the size of the C, it will take forever to get this Q. So that means it will take forever to get this voltage. So this won't settle, so it will take time. And if you remember from time constant, if you write the mathematical equation of this cap, VC will be this, let's call it V source. V source parenthesis 1 minus exponential minus T over RC. Okay? Şuradaki RC bizim time constant'ımızdı hatırlarsanız. Dolayısıyla bu RC ne kadar küçükse devre o kadar çabuk şarj olacak veya discharge olacak. So let's look at here. If RC is small, the circuits will be fast because it will charge quick, it will discharge quick. Okay? So the step response. Step response means input. We apply the input like this from 0 to 1. Okay? So the input is Vs. And output, well, if the RC is small, we expect it charge quick. But if we increase RC, now what we see is degradation in the charge, in the speeds, right? Time domain. So if RC increases, we see degradation in time domain. It will take charge time to charge. Well, in frequency domain, this corresponds to bandwidth, okay? Dolayısıyla hız aslında bandwidth'tir. Sizin bir dijital devreniz, if you are downloading something, okay? Well, why is the speed so slow? Well, because the bandwidth of the channel is slow. The bandwidth is not enough, right? Bandwidth lafı oradan geliyor. Kapasite, bandwidth yetmiyor, değil mi? Hız yavaş. Bandwidth niye yavaş? Çünkü bandwidth 1 over RC. RC büyükse, if RC is big, that means bandwidth is small. That means it will take forever to go through digital circuits. You have bunch of digital circuits, AND gates, NOR gates, blah, blah, vesaire, right? So you apply input, well, it will take forever to charge these intermediate nodes, charge, discharge. So a good circuit is a fast circuit. A fast circuit means RC is small. Either R, not either C, no, both R and C, right? The R is small, C is small. Then when you apply a digital 0, 1, instead of this, you'll see this, right? You won't see that charging mechanism. You'll just instantly see the output. Well, in frequency domain, that corresponds to bandwidth, as I mentioned. Now, small RC means small RC means the bandwidth is big. That means your bandwidth is not here, but your bandwidth is here. Okay, that means all the signals. Remember that the example I gave you, this impulse, you want to host that. All the frequencies you want to go through. So this time domain impulse can only go through if the RC is small. So if the bandwidth is 1 over RC is big. Time domain, we explained to you, this is the output across the capacitance, right? The capacitance is charging. And in the frequency domain, this RC is actually corresponding to the bandwidth. 1 over RC is defining how good is your bandwidth, or how, beginning of the lecture, we gave you the example of fuzzy edges, right? So if it's something sharp in time domain, that means it requires the unlimited bandwidth, right? In the frequency domain. So always remember this example when you think about communications, digital communications, or anything else. So now we jump to the Bode plots, and the Bode plot is important because you can represent your circuit in terms of the characteristics of that circuit, how good you can host it, right? So these are poles and these are zero. So what do they mean? So when we hit a 0, the Bode magnitude rises with 20 dB per decade. So let's say an example. So is this a pole here or a 0?
It's a 0.
It's a 0, right? Because the magnitude rises with slope of 20 dB. Okay, another example. Is this a pole or 0?
It's a 0 because it increased when it...
Perfect, yeah. Because the gain was dropping, right? It was dropping with minus 20 dB. Now the gain is not changing, 0 dB per decade. So you see the increase from minus 20 to 0, right? So that is how you can notice a 0. If you want to notice a pole, well, this one, is it a pole or 0? Question goes to Taha.
I think it's not 0, it's pole.
It's a pole, right? Because the reason is now the magnitude slope with minus 20 dB. It was increasing 20 dB. Now the increase is not there anymore. We don't see any increase, 0 dB. So you see a drop of minus 20 dB. Okay. So this decade means basically 1 hertz to 10 hertz is a decade. 10 hertz is 100 hertz is a decade. It's logarithm, right? So 10 multiplied by, is it decade is 10? Yeah. So multiplied with 10 means decades in frequency. Okay? So if you see a 20 dB increase in the decade, that means here it was, for instance, 10 hertz. Let's say here is 100 hertz. Burası 0 dB ise mesela şurası kaçtır? Mesela burası 10 hertz olsun. Burası 100 hertz olsun. Mesela 20 dB per decade. Dolayısıyla burası 0 dB ise burası 20 dB olacak. Okay? Yani bir decade'de ne kadar arttığını gösteriyor. Okay? So let's go. Well, yeah, simple example of the Bode plot. So we covered this in the previous slides, right? This is the response for a common source stage or a common emitter stage. We have a fixed gain and the gain starts to drop at a frequency, angular frequency of this. And this drop is here 20 dB per decade because we have only one pole. So the question is now, this is the gain, and now we have a pole as omega square. So how would it be different? So this A is GMRD, this is the gain. And as you can see, at frequency of 0, it's 1 plus 0, 1. So the gain is GMRD. But when at the pole, let's call this VP, 1. When S is basically S is J omega, right? When omega is VP, this becomes 1 plus J, and 1 plus J square is at the denominator. So what would be this figure right now? Instead of 20 dB, what would be this decay? How much dB would it be? Şimdi mesela şunun frequency response'unu bulmuştuk. Bunun frequency response'u neydi? Gain GMRD bölü bir tane pol var. 1 artı S VP1. Değil mi? Neden? Çünkü şuradaki S'teki frekans S J omega unutmayın. Hatta S yerine J omega yazayım. Buradaki omega VP1'e eşit olduğu zaman aşağısı 1 plus J. So because it's 1 plus J, the denominator becomes the square root 2 in terms of magnitude. So basically at the pole, this is GMRD square root 2. Absolute wise, I'm talking about. Of course, there will be angle. Of course, there's an angle of 45 here. Okay, but absolute wise, this is the magnitude here. Buradaki omega'yı frekansı arttırdığınız zaman frequency increases. This is the drop. 20 dB per decade. Mesela burası 10 Hz ise gain'e diyelim ki 40 dB. Yani gain 40 dB kaç? 10 üzeri 2. 20 log 10 üzeri 2. Mesela 40 dB 100 gain'i olan yani 40 dB gain'i olan bir amplifier'ınız var. Bandwidth'i de 100 Hz ya da 100 kHz olsun daha realist. Şurada da 1 MHz'de 301'de bir sizin lab sorunuzdu aslında. Şurada 1 MHz'de yani 10 kat yukarıda gain ne olur? İlk bunu cevaplayalım. Decade is 10 times. So 100K to 1 MHz arası kaç? 10 kat değil mi? Şurasıyla şurası. Evet. Decade yani ise decade. Bir decade'de ne kadar düşüyor? 20 dB değil mi? 10 kat evet. O zaman 40 dB olan gain kaça düşer şurada?
Eksi 20'den 20.
Aynen.
20 pardon 20.
Eksi 20 dB cinsinden konuşuyoruz. Evet eğer desibel olsaydı dediğin gibi 10 kat düşecekti. Yani 100 olan şey 40 dB 100 müydü? 100 olan şey 10 kat düştü. 10'a düştü. Desimal. Bu desibel, burası decimal. Okay? Şimdi biz buraya dedik ki bir tane daha pol ekledik. Yani devreyi tasarımını düşünmeyin ama bir tane daha pol ekledik. Ses gitti mi ya? Ses gitti.
Yok hocam sesin
geliyor.
Geliyor hocam.
Tamam süper. Bir pol daha ekledik. O zaman şu 20 dB kaç dB düşer mantıken?
Bir pol daha ekledik. Eksi 20 dB
40 dB mi?
Değil mi? Yani bir leğene bir limon attım. Bir limon daha attım. Kaç limon olur? 2 limon olur. Şimdi bir poldan 20 dB düşüyor. Bir pol daha ekledim. 40 dB düşer.
40
Değil mi? Dolayısıyla 40 dB düşerse mantıken artık devre böyle olmayacak. Yani şurada bir pol daha eklediğim şurada aslında şu gösteriyorum karakteristik pol. O zaman nasıl düşer? Böyle düşer. Değil mi? Mesela örnek. Dolayısıyla mesela o frekansta 40-40 0 dB'de olacaksınız mesela. Okay? So this part is basically important because now we'll have circuits and we have to drive their Bode characteristics. And from the Bode characteristic you have to plot these ones, okay? So this basically, the entire class, the rest of the class will be a circuit. From the circuit, you will find the Bode characteristics from the poles and zeros. And from this Bode characteristic, you will plot it, okay? So that's why I'm explaining you these things. So this one was a common source stage. So it had one pole, so it was simple with that, but it might be a different stage, then it might have the same poles, then it will be this. Or it might have a different pole at a different frequency, VP2. O zaman devrede şöyle olur mu? 40 dB, 20 dB, başka bir pol ekledik. O polun location'ını bulduk. Mesela şurası olsun. O zaman pıt diye bir tane daha düşeceğiz. Neyse anladım. Şuradaki düşüşte 40 dB. Yani burada düşmek yerine burada düşüyor. Dolayısıyla siz aslında şu denominator'da frekansı sweep ettiğiniz zaman P-Spice'a yapacağınız üzere şuradaki denominator'ın ne kadar büyüdüğüne bakıyorsunuz kısacası. Yani buradan bir 20 dB düşüş geliyor. Buradan da bir 20 dB düşüş geliyor. Dolayısıyla okay. Alright. Niye 20 dB? Çünkü 20 dB per decade. Niye? Çünkü siz şuradaki frekansı 10 kart arttırdığınız zaman şurada 1'i neglect edin. Burası 10 düşüyor. Değil mi? Zaten 10 düşmesi 20 dB per decade. Bir daha 10 düşen bir şey daha eklerseniz o zaman 100 düşecek. Yani 40 dB. Okay? So zero works the other way. If there is a zero, now it won't drop, but it won't increase. It will, instead of dropping 20 dB, if you have a zero, 1 plus S V0, now if you have a zero somewhere, this will increase 10 times. So let's say you have a zero, then this goes to normal. And if you have another zero at this point, now it's this, right? So basically zero tries to compensate your circuit back to normal. The poles will drop the gain, okay? It will become more fun in the next slides when you understand it. And let's see. So this Bode came at the Bell Labs 1930s when this guy called Henrik Bode had the problem determining the stability. So when you have a circuit, when you have an input, you need to figure out if the output is stable. Right? Stable means a circuit with a certain input should provide a certain output. But if the output changes, for instance, the output is now this, but after time, 10 seconds, output became this. Then after 10 seconds, output became this. So then this circuit is not stable, right? Because you don't have a deterministic output. You cannot determine HS, okay? Which means V out over V in, right? So the guy basically tried to determine the stability. So he need to understand how stability works with, all these circuits. And in Bode plots, not in this lecture, but when you draw the Bode plots, these bring phases. And these phase drops in a stable circuit. For instance, A plus, this is the gain. Let's call it AG. Okay. So 1 plus, for instance, let's call this feedback factor, 1 AB. So if this BA becomes -1, well, this circuit doesn't become stable anymore because output is, denominator is 0, right? And this -1 means phase of what? What is -1 in terms of phase?
180, I think.
180, right? Exactly. So every pole brings a phase of phase of 90 degrees. Why? Because at the denominator, it is 1 plus J. So at the J omega, let's call it omega pole, right? Right at the pole, it is 1 plus J. Right, so it's 45 degrees. But if the frequency is, let's say, 5 omega p, now J dominates. That means the phase difference is 90 degrees, right? So that means at the denominator, you have a 90 degree. So if I have another pole, you add another 90 degree. So now output has a phase of 180 degrees. So basically, first pole, second pole. At the second pole, if the gain is 1 or below than 1, basically your circuit becomes unstable. So you don't want this point, this gain point, to be 0 dB at this point because your phase is 180, which means -1. And if your gain basically is if your gain is 1, which is 0 dB, then your circuit will be unstable. So you always design circuits such that first pole, second pole, such. So you always design your circuit such that second pole, you have a gain, okay? Rather than 0 dB. Anyways, this is a little bit complicated. I just wanted to explain why it became a need, and this is also answer to Emin's question. Why do we learn these things, right? Well, designing a circuit sometimes, before putting the PSpice or you even put into the PSpice, you should understand why it's not working, why it is not stable, right? So that is the actual technical background behind this. So, and for instance, here is a new circuit saying that determine the poles of the circuits, right? So every RC brings a pole. So this C brings a pole and this C brings a pole. And the important thing is our equivalent, that C does see it. For instance, we might have a circuit like this, okay? And then we have a cap. Well, what is the pole of this circuit, right? So just like remember in the Theorem last year, we covered the circuit and we open this and we look at the direct method, RT. What is the resistance? You kill if there's a voltage source, you short the voltage source. If there's a current source, you open it. If there's a voltage source, we short it, right? Then you look at the RT, direct method, and that is basically your R equivalent. So for instance, here it's quite easy. Why? Because as you can see in the next slide, did I put on next slide here? Yeah. All right. So here it's easy because the cap is here. So just open the cap, basically cut it and check the impedance looking from here to the rest of the circuits. Well, so you short the inputs because it's direct method. There's the RS here and there's the infinite impedance here. Parallel of them will be RS. So the pole here will be 1 over RSC in input pole due to this part. Looking here, do the same thing. The cap is here. Close the cap, check from the cap what would be the impedance. This is open, infinite impedance. This is RD here. This is RO here. Okay, and we assume alpha is 0, so RO is so big, so neglect this. So the impedance, equivalent impedance is RD. So basically CL sees the RD, so this is the second pole. Okay, and if you write the characteristics, right, this will be 1 plus S omega P1 and 1 plus S omega VP2 at the denominator. Okay, and if you want to look at the absolute of this, basically this is complex 1 plus, complex terms. Basically, instead of S, you can write S omega. I just got used to write S J omega. I'm sorry. So when you there are two poles, one pole and second pole, and when we write them, as you can see, this is the absolute value of that because it's 1 and J terms. And this is how you can write the transfer function between V in and V out. And if you plot the gain, GMRD, first pole, second pole, okay, this is how you can plot it, right? So any questions here?
Okay. Yep.
Okay, super. Now another example, and no, not an. Oh yeah, another example. Now we applied V in to the source of the circuit. What kind of amplifier is this? It's a common what?
Common source.
What is the common? What is the part that we are not using?
Common base.
Common base, right? The base is not getting used. You only bias it. The input is at the source, output is at the drain. Yeah. So, and what would be the gain of this? Anyway, gain is still GMRD. You can look at it. You can remember how does common base work. But important thing is poles, right? So let's look at the poles. C in. What were we doing? We were closing the cap and check the impedance. There is RS and there is this impedance here. And this impedance is 1 over GM. If you write the small signal, you'll see it quickly, okay? And the other one is RS. So that's why you multiply Cn with RS parallel 1 over GM, okay? That's the equivalent resistance, R equivalent. And for C, well, it's the same with the previous one. Just close it and you look at the equivalent resistance. Equivalent resistance is just this one parallel this one. Ignore R0, ignore this one, okay? For now, you might not, depending on the question. I say it's so big, you can ignore it. So it's RD, okay? And so we covered common base and we covered common source. What is left? It left is common, what's that? Common source, we covered common gates, we covered common source. What's that? Common drain. Okay, common drain is you apply input to the gate, you get the signal at the source. It's a common drain, which might come in your exam. What is the transfer function for a common drain source follower? Okay, so all right, now we coming to an important thing called Miller theorem. And Miller theorem is quite important because it helps a lot analyzing circuits such as this. So if there's a cap, well, you can ask if this cap is connected here or if this cap is connected here, right? It's hard to analyze the circuit. So in such cases, this genius guy called Miller, I forget his first name, says, well, we can make the circuit an equivalent circuit, just we always do, like twinning. But now it's like Miller equivalence. This equivalent CF can come here as C1 and a part of it can come here as C2. And we basically disconnect the rest. We connect the actual cap, disconnect the actual cap, okay? And now it's easy, right? Because just like similar question, we can describe the pole due to this C1 and we can describe the pole due to this C2, right? And this Miller guy shows the proof here. Normally the circuit is this, right? There is an impedance between two nodes of interest. And we want to make this one cap connected here, the other cap connected here, and we disconnect. So it's a simple nodal analysis. What he says is, well, there's a current going here. So if we make the circuit such that same current goes here, the rest of the circuit is not affected, right? Because you are not really touching anything rest here. You're just transferring, directing this current instead of here to changing the impedance. You're saying it goes here. Same with the node 2. This current goes here. Now we change the circuits in the equivalent model. That current should go here. So that's what he's saying. V1 minus V2 divided by ZF is the current flowing here. Now is V1 over Z1 equal to this current. And same logic, V1 minus V2 over ZF
is this current. And now it is minus VT over Z2. Basically, we can put minus, which is easier to understand. So basically, this part is this current now. And that current should be equal to this current, VT over Z2. Okay. And doing these two equations, now you have these two equations, and then simply you can say Z1 is this and Z2 is this. So you write this and Z1 and Z2 impedance in terms of ZF. Okay. Any questions here?
No.
Wow. Okay, that's good. So for instance, let's say we have a cap here. This cap now will be C1 and C2, right? So a cap impedance is 1 over SC. Right? So what you'll be doing is Z1 is now ZF, which is that cap, 1 over SC, times 1 minus AV. Okay? This is Z1. Well, that means the new cap is this, right? Because the cap is 1 over SC. So this new cap will be C times 1 minus A, equivalent cap. And similarly, same logic here. We have the cap, original cap, SC, divided by 1 minus 1 AV. Well, let's assume the gain is big, or not. Let's not assume gain is big. So now, as you can see here, the equivalent cap will be this. In the Z1, it was this. So as you can see, a cap can be divided into two parts, as this one and this one. Okay. Doesn't have to be a cap. It might be a resistance. It might be an inductance, any impedance. So basically, these are the two important equations. Z1 is original impedance divided by 1 minus AV, and Z2 is original impedance divided by 1 minus 1 over AV. Okay, and usually this A is big if the gain between V2 and V1 is huge. If you have an amplifier between them, right? In the previous case, gain is big. V out, V in. These two nodes actually are output and input, so they have a gain between, right? So back to the circuit. So here, if we make the same logic, well, this will be V out and this will be V in. And the gain between them, AV, if it's like amplifier as you mentioned, as we saw it, that means this will be big, this will go to 0. So we can summarize, if there is a gain between those, Z2 will be actually ZF. But Z1 will be ZF because A is big. It will be ZF divided by minus AV. Okay. So for that cap, the cap example. Yeah. So here CF, we divide it into C in and C out. And as you see, now we can write them as two different capacitances as a function of CF. C in becomes this, C out becomes this. This is 1 over A, right? GMRD is the gain. The 1 plus A plus CF, 1 plus 1 over A minus A, times CF. Okay. So basically, don't forget these two formulas. They are important and you should understand how you apply them to the circuit design. So as you can see, that cap is divided between two. We found C in, we found C out in terms of CF, and we know the gain. Gain is GMRD as if there is no cap, so that we can define input and output poles. Why? Because the cap 1 plus GMRD CF is a new cap. C is the RS impedance. This new cap C out is seeing the RD impedance. Okay. So two poles, V in pole, V out pole. Basically the same logic. We just locate the poles, locate the location of the poles. You can easily tell me, hey, this has two poles. But yeah, what are the locations of those poles? Okay. What is the 3 dB bandwidth of the circuit? What should you do? Question. What would you do to improve the 3 dB bandwidth of the circuit?
Decrease RC.
Decrease RC, perfect. But which RC? This one or this one?
Output'taki sanırım.
Hangisi daha küçükse, hangi RC daha büyükse, değil mi? Hangi RC daha büyükse o omega daha küçük demek. Yani şurada demek. Eğer bu RC büyükse o zaman V'in burada demek. Eğer bu RC büyükse, daha büyükse o zaman V out burada demek. Hangisi olduğunu bulup dediğin gibi Sinan o RC'yi küçültürsek ne olacak? Şuradaki polu alacağız, buraya atacağız, değil mi? Öbür polu da belki buraya atarız. Okay? So Perfect. Anladınız mı arkadaşlar?
Evet.
Sinan anladı. Diğerlerinden ses yok. Taha?
Ben de anladım hocam.
Taha da anladı. Berke? Berke beyni yandı. Tabii 3 saat oldu. Emin?
Yok yani anladım ama biraz değişse devre çalışmam lazım.
Tamam. Süper. Bir kişiye daha soralım. Oytun?
Ben de emin gibi hocam. Anlattığınızı anladım ama hani biraz değişik çıksa karşımda hayret eder kalırım. Ondan biraz üstüne durmam lazım.
Tamam, süper. Tamam, biraz daha bir yarım saatimiz var. Biliyorum yoruldunuz ama öbür hafta da işlemediğim için biraz daha işleyelim. Biraz daha pekişsin. Anlıyorum hocam. Bir dakikalığına gitmiştim. Tamamdır belki.
Hocam output'ta hangi RC büyükse yani onu mu yapmaya çalışıyoruz aslında?
Okey. Output'taki bir daha söyle.
Hangi RC değeri büyükse aslında onu mu azaltmaya çalışıyoruz olarak?
Yani sorduğum örnekte evet. Neden? Çünkü 2 tane polunuz var. You have two poles. One is this and one is this. Bu polların location'larını şurada bir daha çizeyim. Rastgele yazdım. Bir tane poldan işte şu poldan dolayı düştü. Başka bir poldan da daha düştü.
Mesela biri omega ekle, diğeri omega y'de olsun.
Aynen. Biri omega in, biri omega out. Ama hangisi şu anda bilmiyoruz. Devrenin büyüklüğüne, C'nin büyüklüğüne göre, R'ın büyüklüğüne göre değişecek tabii. Hangisi? Zaten devreyi bu yüzden çözüyoruz. We need to figure out if this is V in or V out or V1, V2, right? VP1, VP2, which pole. So after solving the circuit, we figure out which RC is bigger. That means that's that pole, right? Because 1 over RC means smaller. Then, as Sinan mentioned, if we make that RC smaller, we can push this pole towards here. That means gain alabileceğiniz frekansı büyütmüş oluyorsunuz, değil mi? Buraya çekersiniz. Bu burada kalabilir. O zaman ne olacak? Şöyle düşecek, şöyle düşecek. Okay?
Aralığında
yani şu 3 dB bandwidth'iniz şurası. İlk gain'in ne kadar 3 dB, nerede 3 dB düştüğü. Gerisi stability ilgilendiriyor aslında. Çünkü bizim aslında lineer olarak istediğimiz, kullandığımız kısım burası. Gain'in hiç düşmediği yerle ilgileniyoruz en başta. Diğer yerler de önemli. Çünkü diğer yerlerde gain düşüyor. Ama dediğim gibi onlar biraz daha stability'yi daha çok. Alright. Okay. So mesela bu da çok ilginç bir soru. Sınavınızda da belki çıkar. Belli olmaz. Buna ne diyorlar? Cross-coupled differential amplifier. Mesela benim PhD'ye başladığımda ilk çipini yaptığım devre buydu. Çalışmamıştı. Uğraşmıştım falan. Sonra çalıştırmıştık. İlginç. Neden ilginç? Burası V-in. You can actually using this circuit can cancel the effect of undesired positive capacitance. Normalde bir C vardır. Biz bu C undesired'dır. Kapasitans görmek istemeyiz. Eksi C koyamayız değil mi? Eksi C diye bir şey yok. Eksi C koysak enfes olmaz mı? C eksi C kapasitansı etkisini yapmış oluruz. We basically neutralize the effect of the cap. This is also sometimes called neutralization cap. So how this circuit works? Burası mesela differential circuit. Burası V in olsun veya VD olsun. VD over 2 olsun. Burası eksi VID over 2. Burası da o zaman ne olur? Eksi GM, işte bu VID over 2 olur. Şurası da eksiyle çarptığımız için tabii gain de var. RD. Burası da GM RD olur. Çünkü eksiyle eksiyi çarpıyoruz. Okay. Şimdi ne yapmış olduk? Şurası GM RD. Burası VID. Dolayısıyla eksi gain yerine aslında bu devre aracılığıyla artı gain aldık. Şimdi tekrar şuraya bakarsak. Bir dakika. Bunu bir küçülteyim. Şunu getireyim. Şuradaki C 2 not arasında bağlı. Biz ne yapıyorduk bu C'yi? 2 tarafa bölüyoruz. There is one cap here, C1, and one cap at the output connected here, C2. Şimdi şuraya baktığımız zaman C in 1 artı gain bölü CF. Değil mi? Dolayısıyla burada artık sizin neredeydi? GMRD 1 artı A0 CF. Şimdi GMRD gain'iniz de aslında şu 1 eksi A0. A0 eksi olduğu için artıya döndü. Şimdi şu 1 artı GMRD CF normalde normal bir devrenin şöyle bir devredeydi. Yani şurada input uyguladınız. Burada output aldınız. Gain eksi olduğu için A0 eksi GM olduğu için şuradaki 1 eksi aslında şurası. Eksi artı oldu. Tamam. Şimdi 1 artı GMRD CF. Ama burada devre farklı. Şurada input uyguluyorsunuz. Burada artık eksi almıyorsunuz. Çünkü dikkat ederseniz it is connected to the other side of the transistor. So instead of the minus, you are getting plus. So actually the gain from this node to this node is plus. O zaman plus'sa input'taki kapasitans 1 eksi A0 CF impedansından dolayı şu impedans ve A0 eksi değil bu sefer artı 1 eksi GMRD CF olacak. Bir de çok düşük olduğunu düşünürseniz GMRD'ye göre eksi GMRD CF. Yani siz using this circuit you create a negative capacitance, right? Minus GMRD CF. Bu niye önemli? Çünkü burada bu transistörün de bir kapasitansı var. Parazitik kapasitans. Ve biz bu parazitik kapasitansı istemiyoruz. Parazitik kapasitansı nötrlersek devre o kadar hızlı çalışır ki. Çünkü kapasitans buradaki polu yok etmiş oluyoruz. Ne oluyor? Buradaki minus GMRD CF yani şu new CV1 is neutralizing with this parasitic cap of the transistor so that equivalent transistor becomes almost zero. So if we design this, CF or the gain accordingly, these caps, plus cap, minus cap, cancels each other. And what we do is, if this is the input pole, basically we are canceling this pole. That's amazing, right? And this is used in high-speed circuits because why is it high speed? Because we can increase the bandwidth. If we remove this, now the second bandwidth is at this point, the pole, right? So we significantly boosted the circuits, okay? That's why it is used in high-speed circuits. Well, you can look at this, try to understand. Even I was an undergrad, they explained this to me. I wouldn't probably understand it first lecture, okay? So it's okay if you don't understand it right now. But if you understand this question, that means you understood the lecture because the entire Miller, can be explained through the example. Okay. Var mı sorunuz?
Yok
Yok
hocam.
hocam.
Yok hocam.
Alright, okay. Bunu anlattım. High pass filter. Mesela this is an example of the first few slides I presented in the lecture. You remember the Bode amplifier? Actually, the amplifier response is something between 20 hertz to 20 kilohertz. So we need to design it accordingly, right? So this circuit shows that, you have two poles, one pole due to here and one pole due to this one. And this is a design question. So these are given so that you find CI and CL to design the locations of the poles, okay? Basically reverse engineer it. This is given to you and now you design the circuits, okay? If you remember from 301, we use caps to isolate. So you learned the common mode signals in this lesson. Common mode means basically whatever common in that node, usually the DC signals, for instance. So here, the common mode or the DC signal cannot pass through the X. And the reason is, somebody designed the circuits and he didn't know there is another circuit following it. So he didn't really care the voltage here. Let's say this is 3 volts. There's a resistance here. There's a current flowing here. So this node is 2 volts, okay? Around the 2 volts, you have an AC. But this 2 volts, if there is no cap, cannot run this circuit, for instance, because maybe this circuit won't work at 2 volts. Maybe it will want 1 volt, right? So that's why we actually put this cap, because if we want 1 volt, we need to isolate 2 volts from the 1 volt, right? So we need to put this cap. But if the guy designs this 1 volt, designs a circuit such that is 1 volt, that's amazing, right? You just connect it to the circuit so that you don't have to use such a big CI, because this CI is a trouble for your circuits. It is CY J omega. So it actually creates a pole. And because the C should be so big, why it should be so big? Because it should act like short in the AC. We only use it to get rid of the DC. Other than that, it should act short. So every frequency, it should act short. So that means it should be big. And a big cap, that means what in terms of pole? Buradaki cap çok büyükse pole ne olur? This cap is big.
Nasıl çok büyük olduğuna göre 1 bölü sonsuz diye düşünün.
Çok küçük olur. Aynen.
Evet. Yani sıfıra yapın.
Aynen. Pole'un küçük olması neden kötü?
Burada sonsuza...
Pole'un küçük olması bandwidth'i düşürüyor değil mi?
Çok hızlı bandwidth düşüyor. Yani,
evet. Pole'un küçük olması senin şuradaki bandwidth'ini düşürüyor. Yani devrenin hızını da düşürüyor. Değil mi?
Evet.
Neden? Bandwidth ile hız orantılı. Bandwidth büyükse devre hızlıdır. Neden? Çünkü bu cap charge, discharge oluyor aslında. Dolayısıyla bandwidth frekanslı karşılığı bandwidth. Biz bandwidth'in büyük olmasını istiyoruz. Dolayısıyla bu cap'i kullanmamamız gerekiyor. Bu cap'i kullanmamak için bu devreyi düzgün tasarlayıp şuradaki DC voltajını bunu run edebilmesi için tasarlamak lazım. Okay? Hani hatırlarsanız geçen labınızda vardı. İşte VCM bir sonraki devrenin compatible olması için 1.4 olması gerekiyor. Değil mi? Çünkü bu yüzden hani mesela bu devre şuradayken 1.2 voltta çalışıyorsa bu RD'nin mesela ona göre tasarlanması lazım mesela.